we go. So we are recording. So your question was just number 17. So here we go.
Yes.
So that was the Helmholtz equation one, right? So you can see my notes here.
(17) is the continuing with the previous problem, calculate the phase shift delta phi radians of the current with respect to the voltage.
Oh, okay. I was looking at number 18. Sorry.
You're fine.
Oh, yes. Okay. That one. Sorry. So forget that. That one's straightforward. So you have a voltage, which is a phasor. And then you have a current over here, which is a phasor. Let's bring the microphone up here. So remember that your voltage, if you were to write this in polar form, would actually be a magnitude times e to the j phi, like that. And same thing with your current. So if I have a phasor, it's actually this magnitude with an e to the j, well, what do you want to call that? We'll call that theta, I guess. And so the phase difference basically is, if you use this as a reference, then your delta phi, or we'll call this phi1, and I'm going to call that phi2 instead, is just going to be, so if that's the reference, it'll be, I believe it's phi1 minus phi2, or do I have that the other way around? No, it's phi2 minus phi1, like that. So if I use this guy as 0, then this should be a positive phase. That kind of makes sense. So you remember also that the general form of Ohm's law is V equals I times Z. So for a character, I believe it's we're looking at a load, a phase shift. Oh no, it's a characteristic impedance, like that. So this, if this is a complex number, and if I reference this as 0, then this guy is going to insert some phase shift here. So if I solve for I, technically I'm going to get I equals V over V naught, like that. So that should introduce a phase shift into the current relative to the voltage. So whatever you get here is going to be a magnitude and some phase, and your solution is that number there. So just kind of write that down and solve for that.
I think the hard part is that there have been no examples all week. Like, everything's been very abstract, and actually doing an example, I think, would be much helpful than just writing it in an abstract form. And I think that's where I struggled with a lot of the homework, is that there were no real examples. Like, I had to pull out my 3300 and read that book and spend way more time like doing other professors' examples, because we've done 0 examples for the entire last week.
That is perfectly legitimate feedback. So I guess let's do that in a little bit. For now that we're about to start, I just want to do a few quickie announcements here. We have, your homework is going to be due tonight. So I set it up so it's due at 11, specifically so that I can have a good chance to hear some of that feedback today and help you through some of this. I also want to do a quick practice quiz, just to sort of test out the feature. So it's not going to be graded, but there is a quiz posted on Canvas right now. And I'm going to use this as kind of a roundabout way of initiating some conversation and working through examples, and more also to just kind of enforce a little bit of attendance. So it is posted now. It'll be there for the next 15 minutes, and it's just a quick little derivation kind of problem. And I want to see how the submission works with you guys to submit like a formula kind of answer. So it's a little more open-ended and essay. I've also got all our videos up for next week, so you can work through that. And we will have an exam next Wednesday is what I'm shooting for. So we'll have all the homework this week, one review session for next Monday to, just like you say, we'll go through a bunch of practice examples. And instead of just like kind of showing the equations, we can put in some numbers and see how this stuff works out. Okay, so go ahead and go to the Canvas page now and look at that quiz. It should take you just a few minutes, and I'll even give you a short hint here. So as you go through the quiz, just remember that Z naught is equal to the square root of L prime over C prime. And for a lossless transmission line, we have VP. I think I forgot to remind everyone that it's a lossless line. So we're gonna use this expression. And then L prime, C prime. So the idea is solve these two equations simultaneously so that you get some kind of L prime equals some function of Z naught and VP, and then same thing for my C prime. So solve for these two guys here. So this is the kind of quiz style I'm thinking about. And I'd like to do more sort of open-ended stuff on some of the homeworks and maybe the exams as well, because they give a lot more opportunity for nuanced questions and with partial credit and that kind of stuff. So rather than just right or wrong numerical answers.
So I see there's 4 different ones that I can open. I'm not sure which one is the one that we're supposed to open. There's unit 1 quiz, retake, video recording, blah, blah, blah. And there's also unit 2 quiz, video recording, and there's another unit 2 quiz.
It should say pop quiz and the practice quiz is there. Or I'm gonna go to the student view too, just to see
Practice
what the heck is going on with
Oh.
Canvas. So this is why this is not gonna be graded, because I'm not sure if there's gonna be any.
Oh, sorry. Yeah, I saw it. Thanks. In the quiz session. Thanks.
So student view, if I go to quizzes, I should see, yeah, just practice quizzes right there, little pop quiz kind of thing. So as you're going through that, let's see, I have most of the homework set up for next week. I just need to add a couple of extra open-ended kind of questions for the Smith chart. So I figure I'll have that, I'll try and get that posted by this evening so you can get to work on that as soon as you can. And I like your suggestion of doing a little more, I would say numerical, so we can kind of go through various questions together and calculate them together to see what happens. Because you're right, there's a tendency to get sucked into the abstract space, and rather than like, no, wait, let's go through and calculate a few ourselves, because it really helps to get that reinforcement of not just the equation, but let's put in some values and see what the answer looks like.
So I personally actually really like the current style of going through the problem session and you providing formulas. I don't know. I personally feel really comfortable with that.
Well, when it's homework related, I don't want to just like do the answer for you, right? But I'm okay kind of setting it up and saying, here's your equation. But as far as practicing, say for an exam, it's going to be helpful to do a few values or practice problems and put in values and get answers together. That kind of makes sense.
Yeah.
We kind of get the best of both worlds there.
Yeah, that's right. And after we finish the quiz, I don't know if you feel okay with going through question 18. I just want to double check if my thinking process was right.
We can totally do that as well. We've got plenty of time today. Hopefully you all got a chance to at least take a peek at some of the lectures, the new lectures. I think I uploaded all the lectures, but I didn't publish. So that's a thing on Canvas where you can upload the links and all the learning materials, but you have to hit a button that says publish, otherwise the students don't actually see anything. So somebody sent me a gentle reminder last night, like, hey, where's our learning material? So that was not published until yesterday, even though it was up. So I'm hoping you at least got a chance to look through some of that or get a feel for it. But most of today also, I want to just go through some of these concerns and help streamline our process a little bit more. So hopefully everybody get through that quiz yet. Let's see how many answers are submitted. Still Algebra Inc. Yeah, it should take just a few minutes to do it on pencil and paper and then to kind of see what, and figure out how to type it into the form. I guess while you're working on that too, I'll just let you know, I just finished I guess the assignment sheet for lab number 1. So I'm going to post that today as well so that everyone will be able to get started on that Wednesday. And just remember, you should have an early morning session on Wednesday, and I believe there's another session on Friday. So your TA will be the one to kind of lead you through that. I'll probably drop in for the first lab just to kind of help out a bit, both for you and for the TA, just to get a feel for how smooth and streamlined everything is. But ideally, that'll mostly be between you and the TA kind of moving forward. So the idea is I'll kind of post it a little bit in advance. The TA will then work on it the day before to kind of figure out all the quirks, and then she'll be able to help you for both labs after the fact. So that's why I'm kind of deliberately keeping lab 1 a little simple and straightforward, just to help streamline that process. And then we can get a little bit more complicated and involved as time goes on.
Can I ask a question about lab 1?
Sure.
So do we just connect to the Zoom at 7 a.m. on Friday?
Yes, that is how everyone was doing it for the labs. So let's see, it was 10:50, ECE 10:50 and 12:45. Yeah, they had the TA would host a Zoom session, and then you'd all join in there. So I guess I should set that up on campus. Let me make a note of that. So it should, we don't want to have to do separate Zoom links. Set up. One. There we go.
So at 7 a.m., right?
I believe so. So that's gonna be a bit painful for you guys. I hate having to get up at 7 a.m. for this stuff. That's just the only place where you can squeeze some of these labs into the schedule, apparently.
Do we need to do any prep work, like install anything?
Nope, you'll just need MATLAB for this. So you'll want to kind of read the lab a little in advance. There'll be a few little MATLAB codes you have to download, like my little template code. You'll want to make sure you have that. Maybe take 10 to 15 minutes to read through the tutorial. I think most of you are going to be familiar with the FDTD, like you've done it before in 3300, or if you took my class last semester, you did a lot of that as well. But if you're not familiar with the FDTD, you'll want to take maybe a half hour to go over it, at least get the basic idea of what it's doing, even if you're not coding it yourself, that sort of thing. Only 1 minute, my cat is whining.
Thank you.
Okay, so who is still working on the quiz?
Me, just 2 more minutes, 2 more minutes.
Okay, we got 2. Well, it'll be up for another 5. So I should have some option where I can see the results, but apparently it's not letting me. Is there quiz statistics? No. Or has nobody submitted it yet? Nope, we got a few submissions here. I guess it won't let me see it until the quiz is taken down. But I see some people have finished, which is pretty good. Okay, so there's a couple of you still working, that's fine. I guess I'll just open the floor to everyone here. I think you wanted to see. Somebody asked a question. What was that? So question 17, we were looking at that.
Yeah, and actually doing like an example of 17 and making it so abstract.
So you have this notion. Here is some voltage as a function of position. And there is a current as a function somewhere. So usually what you'll have is a forward and reverse propagating wave, but I think the question is just geared where you have a wave propagating to the right, like so. So a simple example, usually we'd like to use nice round numbers. So let's just say there's V naught plus e to the j beta z, like that. So we have to fill in a couple of values here. So let's just pick something. V naught plus is equal to 10 volts. And in principle, I could throw a phase shift on this as well. So let's just do that. E to the j, I'm just going to do like pi over 4. So all that means is there's an amplitude on this wave, and there's a slight offset either to the left or to the right. So this is negative here, so I'm going to say, yeah, we'll do that. Negative pi over 4 like that. So there's some amplitude and some phase there. We also have over here, same idea for the current. So let's use a different color here. So there's my current waveform like so. And it may or may not line up with the voltage. So I'm going to write that as I tilde of z is going to be I naught plus e to the negative j beta z as well. So the question then would be, what is the phase shift between these 2 points here? So the simplest thing to do is like pick a reference like z equals 0, and what you'll get is something like the following. V of 0, V tilde, is just simply going to be V naught plus, which is 10 volts, e to the minus j pi over 4. So we're just, you can pick any arbitrary point you want, but we're interested in just the phase difference. So for convenience, we're just going to pick z equals 0 because that gets rid of some of that. Then we'll have I of 0 is going to be I naught plus, which is times e to the 0-ish, right? So that's just, it is what it is at that point. So I want to know what the phase difference here. So the third piece of information you just need to know is the characteristic impedance. So that is because V of 0 divided by I of 0, or sorry, we'll say V naught plus divided by I naught plus is the definition of my characteristic impedance. So let's give this a value. I'm going to say 55 plus J 0.1 ohms. I'm just completely pulling that out of thin air. So what is going to happen here? So you're just going to solve for I, and what you'll get is the following: V naught plus over Z naught, like that. So there's a number of ways to go. So the first thing you notice is this is in rectangular form, this is in polar form. So you have to make these consistent. So the simplest thing, or what you could do is just slap it into MATLAB and not even care. So let's go ahead and open up our MATLAB window. I can screen share that. There we go. So I'm going to do a quick screen share here. Just give me a second. My screen to, ooh, there we go. So I've got a MATLAB window. So all I said was V naught equal to 10 volts times e to the negative 1j times pi over 4. You just slap it directly into MATLAB like that, and it will crunch on that, and it'll spit back a rectangular value. So you notice it's square root of 2 times 10. Okay, that makes sense. Or is that root 2 over 2? I think it's the 0.707. Oh, so root 2 over 2. That's it. So yeah, that should correspond to the pi over 4. And then we said Z naught is equal to 55 plus 1j times 0.1, just like that. So you don't have to overthink this. MATLAB is more than happy to do the complex arithmetic for you here. So I would just say I0 is equal to V naught over V naught. You notice I am going to get a rectangular value. So I need the phase shift of that. So there's a number of different ways. MATLAB will actually let you do this, just angle of that, and you get this value. You could also do the arctangent. So you'd say the imaginary part of I naught, real. I naught like that. So that should also be the same thing there. Okay, and that is your phase shift in radians, if I am not mistaken. Oh, sorry. So now we got that. Sorry. So you got to now remember that is the phase of I, but it's not the phase shift relative to V. So that's kind of a trickiness in the question. So we can say I naught is equal to the absolute value of that. So I'll get a 0.18. Sorry, I'm writing this down here. And then it's e to the negative j 0.7872. So I'm going to go back now to Zoom here so you can see what I'm writing down. There we go. And this, of course, has units of amps. So this is the phase of the current, and which is a perfectly valid answer. But another question might be, what is the phase difference between the voltage and the current over here? So I would have to calculate the difference. So I'm going to call this, phi2 and phi1 up here. So your delta phi would be, or I'll say phi sub I minus phi sub v. So that would be the phase shift of the current relative to the voltage. So I'll get essentially negative pi over 4 minus whatever that is, negative 7872, like that. So that becomes actually a positive like that. So if we stick that into MATLAB, what do we get? Negative pi over 4. Oh, sorry, I did that backwards. Excuse me. That should have been negative 0.7872 minus the negative pi over 4, like that. Sorry. So minus minus gives me a plus. So negative 0.7872 plus pi over 4. There we go. I get this tiny little value, negative 0.0018 radians. So that is the phase shift of the current relative to the voltage. So be careful not to confuse those ideas in your mind, where I have, you could say the angle of my current is equal to negative 0.7872 radians, but that's only because my voltage also had a phase shift on it. And I can say delta phi, so the phase difference between the current and the voltage, was negative 0.0018 radians. So again, don't confuse those two ideas. There's sort of the absolute phase and then this relative phase over here. So what that implies is, hypothetically, if I defined my zero reference such that this was 0, then these things would become like one and the same. So just got to be mindful of that. So you can think of that as like an offset. Okay? So hopefully that's a good simple example there. All right, so anybody follow along on MATLAB while I did that? So if I'm doing this, it'll really help if you open up a MATLAB window and just kind of follow along a bit with what I'm doing. You'll see, hopefully you can double check my work and so I'm not making any horrible mistakes.
Sorry, where did the pi over 4 come from? That's the beta z, correct?
That was me imposing some arbitrary phase shift on the voltage. So normally what happens is, you might imagine a wave going along. Let's draw that again. The general expression would be V tilde of z is V naught plus e to the minus j beta z, like that. But the idea is 0 is arbitrary. So I could have defined 0 right here, or I could have just as easily shifted it over like that. And it just adds a bunch of phase offsets into this term here. So the way to think of it is, let's suppose I put 0 right there. So I would say V tilde of 0 is simply going to be V naught plus by definition. But this can still be a complex number. So it's sort of just a question of where is 0 and where is my wave striking things. And I have phases piling up on top of phases. So this would be V naught plus e to the j p. So that pi over 4 was me arbitrarily inserting some phase shift into this amplitude here. I just made it up. So there's a number of reasons why that might happen. So a good example is, say, here is a generator with some output impedance, like so. And we go along like this, and then there's a load here. So the question is, where is 0 and what is my phase at all of these points? So usually we define z equals 0 as right here by the load, but I might have my signal referenced over here. This could be, say, V naught plus is, just 10 volts, but I'm going to accumulate all this phase by the time it actually gets over here. So actually what I would say, just so there's no confusion, you would call this V sub G for like the generator voltage. So I'd say V of G is equal to something like 10 volts. So I have a nice 0 referenced phase here, and I've defined 0 over here, but I'm still going to have to accumulate all this phase by the time I get over here, which means V tilde of 0 on the transmission line is going to be my generator voltage times e to the minus j beta L, right? So this is negative L, like so. So, which I could then define as V naught plus. So you see there's just this tendency for all of these phases to creep in on each other just by these waves moving around and bouncing into each other and accumulating phase offsets. So hypothetically, I could have defined this with some arbitrary phase to reflect the fact that this wave had to travel down this line. Or what you could do is offset all of that and just say, I'm going to say this guy, I'm going to impose a phase offset onto my generator so that this becomes 0. It's all just a lot of bookkeeping. It's a little confusing, but it's mathematically consistent.
I guess my my struggle, I apologize because I guess I just don't follow. My rationale originally was we're trying to figure out what the phase shift of the current with respect to the voltage is.
Mm-hmm.
Current and voltage are kind of, well, let's say I wanted to set my voltage as a 0 point,
Mm-hmm.
a tare point or something. So I would set Z equal to 0, right? And then I would calculate I's phase shift with respect to the voltage.
Yes.
I just wonder why we would ever choose a Z that is not 0 if we're trying to find a...
You could do that, but then the question is, what is my generator over here? Will have a phase offset relative to my 0, right? Because there'll be a time delay by when the signal here is generated to when it finally lands over here. So you could do that and define all of your phase origins as being 0 here. But then if I were to ask you what is the phasor of the generator over here, you'll have to account for that phase again. So try as you might, these phases are still going to sneak in one way or another. But you're right, you could have arbitrarily set this to be 0, and that would be fine. But I could just as easily ask you what is the phase of the voltage here at minus 20 centimeters, say. And now there's a phase again you have to worry about.
I see. Okay, so you're addressing the general case where the problem asks for an offset offset distance rather than just making it easy and allowing us to do a 0 for the voltage.
Well,
okay.
I can try. In practice, you'll try your hardest to pick the most simplest 0 reference, but try as you might, there'll be so many phases you have to keep track of anyway, just depending on what you're doing. So it's a good question, like, why don't I just define this as 0? And you can, but then depending on what you're doing, you will have to account for something again, no matter what. So I'm just kind of giving you some practice with that notion of, suppose this thing isn't necessarily 0, so find your phase shift between your voltage and your current. But I think in the homework, I specifically did make this 0, so that all you had to do was calculate your I equals V over Z here, right? So that had a phase of 0, so this just inserted a slight negative phase, I believe. All right. However, I think what also happens is, so it doesn't actually give you a negative phase though, because Z naught is the square root of R plus J omega L prime, or G plus J omega C prime. So if I added a real resistance here, I think what happens is you get a negative value on your imaginary Z, which when you divide becomes a positive phase shift. Does that sound right?
Yes, that is correct.
Okay. So then there's a lot of pluses and minuses that pile up. So it's pretty straightforward stuff, but you can see how it's very easy to accidentally miss a minus sign or two along the way, which I guess you could also say is a wonderful case to make these exams more open-ended. But at the same time, one of the fun things about these numerical problems is if you just type the expressions correctly in the MATLAB, it will handle all of that for you. And so you saw this example, you can just feed these numbers straight into MATLAB and it does all the complex arithmetic for you. So that's why I kind of have mixed feelings when we start doing some of the more advanced Smith chart stuff and the input impedance. Like you can just dump this into computers and they're more than happy to do the complex arithmetic for you. But there is still some value in understanding a lot of the intuitive motions around the Smith chart there. So we're going to touch a little bit on the Smith chart. My philosophy is to treat it more as kind of an intuitive visual metaphor for what's going on in transmission lines rather than have you like solve shunt stub problems by doing all the circle matching type stuff. So we'll kind of see how that develops later in the class. But Friday, for that lecture, I did a nice sort of PowerPoint slide where I tried to focus just on the intuition of the Smith chart and just what it means for the reflection coefficient to move around. Because it's extremely imposing to look at this thing at first. But if you just remember, this is a polar plot of the reflection coefficient, and all you do is just dance around depending on how you move the loads. And there's rules to how these lines track around depending on what you do to your transmission lines. But that's for a few later days down the line.
Oh, a quick question. I'm just wondering if the exam is open book.
Oh, absolutely.
Oh.
Open note, open book.
Okay, thanks.
Yeah. The only reason I would do like close, yeah, it would make no sense in a class like this because there's just so many equations everywhere and nobody just memorizes this stuff. And in practice, when you're out there on the job, you will have your textbook right there on your desk, ready to work with for any problems you have to solve.
Oh.
So I'm a big believer of just open book, open note type stuff.
Alastair asked if it's open MATLAB too.
Oh, MATLAB, yeah.
Oh, really? Oh my
I was
gosh.
thinking
Oh.
that.
Okay, great.
Because there's just, it's going to just be, here's some equations, see if you can solve. And I'm debating whether or not it would make sense to do like a graphical kind of thing, like plot, like for homework, it makes sense, create a graph of X versus Y kind of thing. But if you've got MATLAB there, I'm wondering if that might be a good kind of open-ended essay kind of question where, you set up a transmission line and you ask a few basic questions about magnitude and phase. Then you can say something like plot the input impedance as a function of this distance away from the load, say, and create a plot in MATLAB and submit that as your answer there. It only takes a few seconds to write the code, and then you would just use like a file upload, and it's a nice little graphical solution as well. So
if you were to include things like that, will you give us some similar examples during review sessions so at least we can practice some of the similar plotting codes that we might not use as often? Like
that is totally legitimate. So that's what I'm thinking is next Monday we'll just after I've got the exam kind of put together, we'll just do practice problems and we'll kind of go through values together. And I'll share my screen on MATLAB to show you how I do some of that stuff as well.
There's no class next Monday because it's Labor Day.
Oh, crap, you're right. So I think then it will be Wednesday as a review session and then the exam is on Friday. Is that what I put in the schedule? Yeah, I think that's what I put in the schedule here.
I have a question about the homework. It's kind of a two-part question. Maybe it's just me being confused about things. I just want to make sure I'm doing it correctly. So when we do the characteristic impedance and you're adding in the R prime, G prime, the equation should be a real part plus an imaginary part. And so if there's a negative, when we put in the imaginary part, so instead of being real plus imaginary, it's real minus imaginary. When you ask for the imaginary part, we would put the answer as negative number, correct?
Yeah, so when you actually carry this calculation out, what you will get is something of the form ZR plus J Z sub I, and this Z sub I can either be real or positive or negative. This should always be real, I'm pretty sure. It wouldn't make sense to have a negative resistant component unless you have like some sort of weird amplifying thing happening, which can happen, by the way. There are physical systems that would actually manifest as like a negative resistance in a sense. What would happen then is instead of an exponential decay, you would have an exponential explosion. But it's a valid solution to the wave equation. But you're right, this thing will either be positive or negative, depending on what values you put in.
And then my other question is when we do, so problem 16 says, calculate the propagation constant beta. That's where we're doing that's the gamma equation instead of the two divided by each other.
Yes. So there's Z naught and then there's gamma here. So I'm going to say gamma squared is equal to R prime plus J omega L prime, G prime plus J omega C prime. So there's your gamma. And if you take the square root, it just makes that kind of nasty. And then, of course, Z naught is this other guy here. So I already wrote it down. I'm just going to write it down again real quick. G prime plus J omega C prime. So don't forget this equation. You should just kind of really remember these equations here. And then remember also that gamma, when you take the square root of this thing, it will come out as a real and imaginary bit. So you could hypothetically say gamma sub R plus J gamma sub I. But these parameters are so important that they're usually given their own symbols. So we write this as alpha plus J beta. So if I specifically say beta to kind of clarify that, then you know this is what I mean.
And that's does beta have its name, or is just gamma the propagation constant?
We kind of talked about this last week, where technically wave number and propagation constant tend to get used interchangeably.
I think that's the confusion, because when you're reading the book, they bounce around with all different naming.
Yeah,
because one's lossless, the real part can be ignored.
Yeah, for lossless, when you have a lossless line, remember that the alpha goes to 0, and these things basically almost become synonymous, right? You just have that J there you have to remember.
Will you maybe go through question 18?
Uh-huh. So question 18. I did this, I think we did this a couple days ago, but it wasn't quite as explicit. But here's the Helmholtz equation. Minus gamma squared V is equal to 0. So this is just a generic differential equation. And there are many possible solutions to this thing. So the idea was, oops, sorry, hang on a sec. So the idea was we postulated some possible solution. V of Z is equal to V naught plus e to the minus J, or I think we'll just say gamma Z, sorry, plus V naught minus e to the plus gamma Z, like that. So if I'm using, it's gammas, the imaginary bit is implied there, whereas if it's beta, you have to put a J beta. So sorry about the scribble there. So this is a possible solution representing a wave traveling to the right plus a wave traveling to the left. So the question is, does this function satisfy this differential equation? So all you're doing is taking this and substituting into here and proving that you get a true expression.
Yes, that's right.
Yeah, so this is just one of those quirks in partial differential equations where oftentimes you kind of do have to guess what the solution might look like. And your proof that it works is to just shove it in and see if you get a correct expression. Because there's many, many possible forms of the solution, and the correct value depends often on what particular excitation sources and boundary conditions you have in your system. So this is just a kind of an abstract exercise in how that will work, that you just take this and you shove it into here, and lo and behold, it will give you a correct result. So all you have to do is prove that this satisfies this. And it'll seem a little tedious now, but I promise when we start doing like some of the waveguide stuff, this sort of thinking starts permeating a lot of that, where you just have to exercise some of that clever insight because you'll have a system like this with boundary conditions, and there's no set algorithm per se to derive the solution, and you kind of have to assume the form a little bit with some insight to get the right answer. So that's kind of the aggravation, but the fun in solving PDEs, I guess.
Yeah, sorry, because it has been like a while before I did partial, double partial fraction. So I was wondering if you felt okay with like doing that for a bit, or
If I what? Say that again.
if you feel okay with doing the partial fraction, partial derivative thing, like double partial derivative thing for a bit.
You mean you want me to go through that right now, or?
Yeah, if you're okay with that, because I haven't done that for a really long time, and I kind of just want to like get a hold of
The
it.
first step then is you look at this, and I'm just going to take the partial derivative with respect to z of everything there. So what you find is partial v with respect to z is equal to, and you just carry out the derivative, so I get a negative gamma v naught plus e to the minus gamma z plus gamma v naught minus e to the plus gamma z. So then you do the derivative again, partial with respect to z.
Oh, I got it, thanks.
Okay.
Yes.
So then that repeats itself and you just get this gamma squared term. And then if you factor it out, you see that it'll satisfy this original equation.
Okay,
Only
thanks.
like 2 or 3 steps. And 90% of this is just me kind of trying to get a handle on how to have you do open-ended things. I think I like the fill in the blank because it should give you the option to use the formulas. So you shouldn't even have to like take a picture of your paper now that I think about it. But it's already done. Most of you have submitted it. But the idea is you could just type some text, insert an equation using the text field, and so on, and that would make a little bit better for these kinds of problems. Oh, another quick note I forgot to mention. I will be posting homework 2 in a minute, but as some of you may have realized, I tend to flub my answer key a bit. So I've got a note, if you discover a bug in the answers, because they tend to creep in a bit, if you're the first one to discover it and point it out to me, I will give you like a couple extra bonus points to make it worth your while. So those of you who start early are more at risk to struggling because the answer key may be wrong. But if you point it out to me, you get a few extra bonus to make it up for it. So if you're a little later on the start, then that's okay. You'll be a little less likely to run into problems, but you won't necessarily have that opportunity to be rewarded with a few bonus for catching those. So just keep that in your mind. I am not infallible. So if you are really sure that your answer is correct and my key is wrong, send me an email and I'll try and fix it as quick as I can. So there are 2 or 3 of you who spotted some bugs in the answer key, and I've given you some bonus points back.
Is that what happened between question 14 and 16 last night?
Yes. In the question, I think it asked for alpha equals, oh, what was it? There was no, that wasn't it. What was the problem again? Oh, yeah, so it was the R prime, excuse me. So it said R prime equals 1.0 ohms per meter. In my answer key, I accidentally put in 10 ohms per meter. So I misplaced the decimal point. So everything was off by a factor of 10 for those questions. So
Oh, I see.
it was pointed out. I made the correction as quickly as I could, and it should have been not a problem for most of you. So the one of you pointed that out for me, and I gave some bonus points back. All right. So, and there was one student, for some reason, they were getting the right answer and it was not accepting it. I cannot explain why it was doing that. So if you run into some kind of weird technical glitch, like where you're sure the answers are right and I'm telling you, then you just let me know, and when we go back and grade your homework set, I will just artificially input the correct or the right score for you. So it's not the end of the world if you're running into trouble. But I do apologize if that sort of thing happens. I know it's frustrating, but I am doing my best to avoid those things when they kind of happen inevitably. So I appreciate your patience and for pointing out for me. So I think we got about another 5 minutes left. Are there any other major questions? Your homework is due tonight, like around almost 11:50 at night, I think is what I put. So basically midnight. And so that's my way of just saying, this is your chance to ask all the questions about it. And so get a good start on those lectures. They're all posted now. You should see them on the Canvas page. There's some nice little video demos. And I will be posting your lab shortly as well. So if there's any other questions, you're free to go now, or you can ask them and I'll answer them for the next few minutes.
Yeah, I got a question still about the problem 17. I put it in MATLAB. I think it's pretty straightforward. Just the voltage over the Z naught. Voltage is 1 volt. Z naught is that complex number, and angle of that. And it's not accepting the answer.
Oh, what number did you get?
0.007.
0.007?
Yeah.
Does that sound like the correct answer?
MATLAB's rounding too much for you.
Yeah, but even if then, like, no, sorry, 0.007 times e to the power minus 4.
I'm pulling up my answer right now here. So if I run this guy. So you're talking about the phase shift.
Yeah, so it's a voltage, which is 1 volt over
the answer should be 0.008 or 8 times 10 to the minus 4. So it's 79577. So it sounds like you're rounding down by a huge margin. So
I see. Well, thank you.
So that was something I noticed. A lot of answers were heavily rounded. So I tried to go back and fix a few of those as well in your answers. But be careful about the truncation or your significant digits there. That can bite you a little bit. So I think what I'm usually doing is using the third significant digit as a margin of error, plus or minus 1 there. So that's another thing that could happen. You might be really close, but if you accidentally round or truncate some digits, you might get a wrong answer as well. So be careful.
Thank you. Sorry.
Just to let the class know, so when you solve these problems in multiple steps, so you solve for one thing, round to 3 significant figures, then you use that number to solve for another question, once again rounding it for 3 significant figures. Then for the final problem, you round it to the 3 significant figures again. You have this compounding rounding error that you've brought through. So each problem, you should solve it symbolically and solve it completely each time. And then that way you don't bring forward these rounding errors. And that would have prevented you from receiving that 1,000th rounding error that you saw with MATLAB.
Yeah, that's a very important practical point too, because if you're actually designing a real system, you don't want these little rounding errors to accumulate, because they can manifest as a significant deviation from the truth if you aren't careful. So I was debating with myself whether or not to kind of add a little bit more padding into the solutions, or just kind of leave them a little more on the precise side. And I'm a little biased towards making them a little extra precise, just to give you good practice in not overly rounding things, because that can cause troubles in a real design if you aren't careful. So exactly what you just said was solve it symbolically as much as you can, or use variables in MATLAB so that it's preserving precision out to like 15 digits with each operation. But don't just take a number and then truncate a digit or two before going to the next step. That will accumulate a significant amount of error, which is very bad.
Question on the sign of that answer of question 17.
Mm-hmm.
Is the current not lagging behind the voltage and therefore negative phase shift?
So let's see, I got calculate the phase shift of the current with respect to voltage. So that is just a number, and I believe, so we have was it a positive value there? What do we have here? So that is the absolute phase I got was a positive number. Does that sound right?
I'll double check my work. I may have done an error.
Because I just used raw expressions in MATLAB and variables, and I got a positive phase shift there. So that would imply my Z. So if that's right, my Z naught should have a negative value on it, right? Yeah, so I think it asks you to do the, oh, nope, I don't actually ask for that. So I was gonna say, some other problems there might have done that. But you break up the characteristic impedance into a real and imaginary value. So what you should see is a slight negative value on the characteristic impedance. So Z naught is Z real plus J Zi. So if that thing is slightly negative, then you'll get a slight positive shift in your current because you're going to be dividing. So I is V over Z naught, like that. So if this is negative, that implies a slightly negative phase on the impedance, which you divide becomes a positive shift. So that would imply the current is leading the voltage. And that is a question I might ask on an exam when you do the phase shift. Is it leading or lagging? Okay, so if it's a positive phase shift on your current, that means it's leading the voltage. So if you were to actually plot them sort of side by side, so if that was the voltage, then my current would look kind of like this. Let's see if I can draw this a little bit like that. Okay, sorry. So that would look like a slight lead in my current relative to the voltage. So we'll call that V, and then this is I. So a negative imaginary value on my characteristic impedance will imply a leading current. So those are some nice, quick little multiple choice questions to be mindful of. And they're a nice way of testing your understanding of the interpretation of some of the language, because this sort of thing is very common.
So I got a question about like the whole class working together. One of the things that I really love about in-person classes is building study groups and collaborating with other students to help each other work through the homework. Mm-hmm. I've had other classes use Discord servers as a way of opening up a channel for students to talk to each other. Is there something in Canvas that we could use? Is the class okay to use Discord? Does anybody else have some suggestions?
I'm not terribly opposed to you guys doing groups together when you're just doing the homework, as long as you're genuinely being engaged in it. And there's kind of a concern for turning in work that wasn't necessarily yours or just copying, which can happen easily because it's very hard to police that for quizzes and stuff. But as far as exams go, you'll definitely have to do your own thing. So I feel like you'd only be hurting yourself if you rely too much on others to get your homework done. So as long as you are very sure to take part in the group and submit your own answers and understand what you're doing, then that's totally fine because it will manifest as good scores on your exams. So you can do whatever you want as far as offline studying together. I believe, I don't really know what Canvas has. It has like these discussions, but I don't know if they're like live sessions that you can do. So I'd be interested in hearing some feedback on sort of like any sort of community sites where you can come together and set up a Zoom session or something, or a Discord server, and just work on your homework and labs together. Well, at least like with labs, you'll have the TA on the Zoom session kind of thing. But I don't know, what do you think? Any good ideas there?
So like one of the options is we can send private messages through Canvas to different classmates, ask their contact information to have small group sessions where we can just create a group chat. Like,
as students, can you create your own Zoom meeting?
Yeah, anyone can create a Zoom meeting.
I mean, that kind of works. You don't have to use Discord, do you? Or if you just do a Zoom session together, you can kind of work together all you want.
The advantage of Discord, though, is that we can see who is online, who is available. It's kind of like Skype, that the availability part.
So it has a little green dot of like, hey, 4 students are online, let's all get together kind of thing.
Oh, we can create a Skype group? I don't know, just...
I have both Skype and Discord. I use Discord a lot more, though.
Interesting. Yeah, I would say by all means, if you want to set that up, go right ahead. And as long as you remember to kind of do your own work and submit your own answers, don't just, copy down what someone else says the answer is just because it's correct. Because that will hurt you in the long run. You won't be getting that understanding, and then you'll be stuck there doing an exam and you won't quite know what to do, and it will bite you in the end. So that would just be my one caution to remember is by all means work together, collaborate, but when you fill in that number on your homework sets, make sure that you kind of put your pen to the paper and figured it out yourself and typed in the calculator yourself to see what was going on. Does that cover make sense?
Yeah, I was thinking if you don't mind to maybe create a Discord link and we can just all join it, and you can actually monitor what we the information we share.
I can't do Discord. I could do the odd Zoom meeting from time to time, but that's sort of what these sessions are right now, right? So I don't know.
Okay.
So for that sort of thing, that would be you on your own time there. And if you email me stuff and I get back to you in real time, that works too. All right.
So I will say that you have been very responsive when I send you emails and then you email me back and whatnot. So that is very helpful.
Yeah, I get an instant ping on my phone usually whenever you send me stuff. So as long as I'm not in the middle of something important, then I can usually respond pretty quickly. I think one student emailed me like at 9:30 last night about some question. I was like, I'd love to help this, but it's bedtime, dude. Sorry. So I hope, I forget who it was, but I hope we've answered your questions today in the review session. But yeah, so like there are obviously some limits to what I can do, but if it's Tuesday in the afternoon and I'm just working on stuff and I get a ping, I usually do my best to try and answer it as quickly as I can. All right, so if there's any other questions, we can go ahead and sign off. Speak now or hold your peace for the next couple days, I guess.
I have a quick question. I just saw like in-person or remote survey about the lab on Canvas. I don't know if it's like a really old. Is that still a valid survey?
I was initially, because what happened in 3300 is Steve Blair had a lot of students who wanted to do in-person labs and not do remote labs. So what he did was he sent out just a class survey, like, are you comfortable coming in person? Like, we could set this up, but we have to all remember to stay 6 feet apart and wear our masks and all of that fun jazz. So that was me asking you guys as well, are you okay with maybe having one remote session versus one in person? And the main advantage to that is if we have an in-person lab, then Mel doesn't have to buy quite so many of those lab kits for you. You would just check out a kit, work with it for the lab in person, and then you return it. For the remote labs, you have to get your own kit, and that's a little harder on Mel because we're trying to order all these things. And then you have to be kind of remote for this stuff. You don't necessarily have quite as much access to equipment, so you're stuck with whatever you get in that kit. So I was hoping to get some feedback there. Nobody really seemed to answer that.
Yeah, sorry, I did not notice it until today when we were doing the quiz, and I realized there's a link. I never discovered that magical survey. So I'm just wondering if you still want to hear our feedbacks regarding.
So actually, it's not too late because Mel is still trying to get these kits put together. I think there's a limit of like 5 per purchase, so you can only buy a handful at a time. That's why it's taking so long. But if there's at least half of you, or at least 5 to 8 of you, I guess ideally I'd need about 8 of you to want to do the in-person to make it worthwhile. Then we could actually do one of the labs. We can shuffle you around where we'd say have the Wednesday lab would be in person or the Friday lab, depending on which we prefer. And then we would just go to the lab on campus and we'll just have to wear our masks and stay far away from each other, and we'll have an in-person lab. So my idea was I would only do that if there is a large, substantial number of you who are comfortable going to campus and being exposed to all of each other's filthy germs. So that was the idea.
Yes, that's me. Yeah, I'm glad that you readdressed it. Hopefully, I don't know. Yeah, let's see.
But so is that you would prefer an in-person lab versus online?
Yes, I would totally prefer in-person lab.
Okay. So, okay, that's good to know. And if there's at least like 5 or 6 more of you who honestly would prefer that, we could probably make that happen.
And the in-person lab will actually be using proper equipment and not the miniature ones. Or will it
So
also be the
that's
miniature ones?
another sort of sticky question, because we want the labs to sort of be uniform. So the way Steve Blair set it up was everyone was using the kit still. You still had some access to like the lab computers. So you wouldn't necessarily have to install so much software on your own laptop there. But for uniformity, you all kind of have to use mostly the same equipment. And I think the idea is one of the labs, I think it's the electronic lab or the power lab. One of the labs is a very large lab. It doesn't necessarily have all the network analyzers in it, but it's big enough to space you all out. So you're all at your own little desk fortress hiding behind a bunch of computers, and no one has to get within 10 feet of you. So that was more of the idea. So the equipment would still be the kits, and you would use the lab computers for a lot of stuff. You wouldn't necessarily have to install anything on your laptop. But as far as, we wouldn't necessarily use the big expensive network analyzers. But then you also don't have to worry checking out the kit or putting down the $50 deposit. So if that sounds appealing, let me know. And I'll even send out an announcement as a reminder to see if anyone's still really interested in that. But I would need like about half of you, so 7 or 8 of you, to make that worthwhile.
Okay, thanks.
All right. Okay, any other last minute questions before we sign off?
Not a question, but a little bit of input on the in-person lab.
Yeah.
This year, I have not purchased a parking permit, so
Oof.
I've all my classes are online now, except with the exception of the senior project, and I'm kind of going in after hours so that I don't get ticketed. So my vote for not doing an in-person lab is not because of fear of the germs or fear of complications, but I'm just saving $200 because the university wants to take $200 from me, and I'd rather not let them have that.
You like time parking, like going to the pay lot?
It's 140. It's 140 per semester.
There's also
140.
buy a 4 or 5 hour pass through the campus play. Like you would just have a U-Pass for that like 6 hour window. That's what I've been doing when I TA the lab, because
I think that would just be like what, $10 a day, or if that, $6 a day.
it's $6, and I calculated it out for the 2 labs I'm TAing. It's cheaper for me to buy 2 of those a week than 140 for the entire semester.
Oh, there you go. So that's a nice compromise there.
Oh, I think I did it before. If it's only like 4 hours of the day, sometimes it's like even cheaper. Okay, I forgot how much.
Yeah, the lab would be about 3 hours. So you need like a little 3 hours plus change. So probably a 4 hour block to really make that work.
One could also park at Trader Joe's and take the train up. You got free UTA with your U card.
I personally take bus.
No, that's good feedback. And it might make my life a little easier if at least half of you really want to do an in-person session. Because if nothing else, it's just 10 fewer kits that Mel has to process, and we can just check them out there when you show up. But we are prepared for the eventuality that you'll all have to be remotely anyway. And a big part of the motivation for that is because the university does have some mandate for like halfway through the semester, we're going to have this 2-week block, I think, where everything has to be online anyway. So I need to go back and double check that. So there was some issue of like, what's the point of having this in-person thing when they're just going to force us all online against our will, no matter what. So there was a little bit of that back and forth, but we could work the lab schedule around there. Like there's way more time in the semester than really labs to fill it all. So we're only set up to do like 5 or 6 labs total for this particular class. So if there's some issue like that where there's a block of just all online, we could just maybe not have labs, or we could do just another digital simulation kind of lab, that kind of thing. There's a lot of flexibility there. But yeah, go ahead and fill out that survey for me. I'll send out another announcement about that as a reminder to everybody. Okay. Thanks, everybody. I'm going to stop recording now.